Okay, good afternoon or good morning, depending on where you're at. My name is John Cusimano. I'm with Exida, and today we're going to present a webinar that is a repeat of a presentation that I delivered last week at the American Petroleum Institute IT Security Symposium that was held in Houston. The topic of the talk is on how to understand the real risk of cyber vulnerabilities in industrial control systems or industrial processes, and how to use a process that we call a cyber PHA, or you might want to call it a cyber HAZOP, to be able to identify the highest risk areas in a control system so that you can properly design mitigations and apply your resources in the most efficient manner to address and mitigate those risks and avoid the unfortunate case of either under-designing or over-designing cybersecurity mitigations by, in fact, taking the time to first understand the true risks to the process so that you can properly mitigate those. So that's what we're going to talk about, and how we can borrow from the engineering practice and discipline of process hazard analysis that's been used heavily in the process industries, such as oil and gas and petrochemical and chemical, to be able to identify and rank the risks in a hazardous, potentially hazardous process. We're going to talk about how we can apply that technique and those tools to performing cyber risk assessment on control systems, and the advantages of using this well-known systematic approach and well understood by engineers that work in the process industries to be able to perform this type of assessment. So a little bit about myself. I am the director of Exida's ICS Cybersecurity Business Unit. My background is in industrial automation, but with a specialty in the area of functional safety and cybersecurity. Particularly in the more recent years, I've focused my efforts entirely in the field of cybersecurity of control systems, vulnerability assessments, cyber risk assessments, and the testing and certification of products for cybersecurity. Been very actively involved in a number of industry associations in this area, particularly the ISA 99 committee and the ISA training program, as well as several private and public sector efforts to mature the industry in the topic of industrial control system cybersecurity. Before we go further, I'm interested in knowing, those of you who are online here, is how many of you already have heard or are familiar with PHAs or HAZOP processes? And I'm going to make sure you can see the results here. So yeah, it looks like a large percentage, of over 92%, 84% or so. A high percentage of the people on the line here actually have familiarity with that, and that's good, because what we're going to talk about now is a little bit, for those of you who aren't, we'll just kind of recap quickly the HAZOP process, so the PHA/HAZOP process, and then talk about how we can apply this process or this type of process to performing a control system cybersecurity risk assessment and some of the advantages of doing that. So a process hazard analysis, or PHA, it's an organized, systematic assessment of the potential hazards associated with an industrial process, such as a chemical process, oil and gas process, refining, and so on. And they've been used for decades to help companies that own and operate these facilities to understand and rank the risks in an industrial facility so they can be properly mitigated. In fact, PHAs are mandated by the U.S. government, by OSHA in particular, in the process safety management regulations for highly hazardous chemicals. These are really important in decision making for management, for operations, to understand where the potential hazards are and to be able to design safeguards that will reduce the likelihood or the consequence of an unwanted or unplanned event. These are a very important part of the safety program for any facility. The idea here is to be able to identify and analyze the deviations and the causes of those deviations that could result in a fire, an explosion, release of material, loss of containment, spills, and so on. The focus of a PHA is on the actual process equipment, such as the pumps, the vessels, the tanks, the piping, and so on, as well as the instrumentation associated with that to some extent, the utilities, water, steam, and so on, and human actions, the actions that an operator, for example, could take to mitigate. PHAs generally are not focused on the details of the automation systems that are behind a lot of this equipment. In fact, generally are not. There are actually different ways to perform a PHA. PHA is a very general term. There are a variety of different techniques available, such as checklists, what-if scenarios. The most popular, particularly in North America, is the HAZOP, Hazard and Operability Study. Also techniques like failure mode and effects analysis, layer protection analysis, fault tree analysis are all forms of process hazard techniques that can be used to conduct a process hazard analysis. So we're going to focus a little bit on the HAZOP because it's pretty much the most popular method in use today, particularly in those industries that I've spoke of. So a HAZOP, or a Hazard and Operability Study, again, is a very structured, systematic approach to examining either an existing facility or a planned facility to identify and evaluate those potential hazards that could represent risks to the operation, either to personnel, equipment, operations. So we're looking at risks in terms of financial risks, financial loss, like downtime, loss of production, but also health, safety, environmental risks, and oftentimes even things like corporate reputation are looked at. A HAZOP is a qualitative technique, meaning that it is not, you're not dealing with precise numbers like probabilities. We're dealing with more qualitative terms like low, medium, and high. And it's based on a principle of identifying deviations in the process and then using guide words to help understand what the different causes might be of those deviations. And I'll show you an example. A HAZOP is best carried out by a multidisciplinary team, that is a team made up of people, a variety of people in a variety of roles that together have a good understanding of the process, probably the process chemistry, as well as the potential hazards, the operational aspects of the system, the design, how the system's designed, and also people who have a good handle on risk and risk management. So the starting point for any good HAZOP or PHA is to have a diagram. Usually we're going to start with a PNID, a piping and instrumentation diagram, that illustrates for us the process, the equipment, and how it is configured, as well as how it is instrumented. So in this example here, we're going to look at, we've got which is a very simple P&ID diagram showing a chemical reactor with an agitator motor to mix the chemicals. We've got a couple feedstocks that are put into the reactor. It's got a steam jacket to presumably heat, and a discharge pump and a vessel for the final product. And of course, a number of different valves, instrumented valves. Fairly typical, simplistic but typical. And then the process of going through the HAZOP then is to identify. You start by identifying nodes in the system, or the different elements. So say the reactor, or a pipe, or a pump, and you look at deviations. Guide words that would say, for example, the flow. Could it go? How could there be a problem with flow? Well, it could be too high. It could be too low. There could be no flow. There could be reverse flow, and so on. As well as it could be contaminated. Pressure, for example, could be too high, too low. You could be drawing a vacuum, and so on. So by using this systematic approach of asking the group questions as to what could go wrong, what are the failure modes, and then getting to what would be the potential causes of that, we can go ahead and complete our HAZOP. So the HAZOP, there's a number of different ways to document it. There are software tools available on the market to help guide a team through the process and help generate some of the documentation. Or you can simply document it in a spreadsheet. This is a very simplistic HAZOP that looks at the deviation, in this case agitation. Guide word in this case is no, so no agitation. And what could cause that? Well, there could be multiple causes, but in this example, it's that the motor drive fails. What are the consequences? Well, it could lead to a non-uniformity and possibly a runaway reaction with an explosion. What safeguards are already in place to prevent this? On this example, we say there's a high temperature and a high pressure alarm in the DCS, as well as the ability for a chemical short stop to be put into the reactor to stop the reaction. Then the next column is recommendations. So if, and this example does not show an assessment of risk. Most actually would. And then if the risk is too high, then the team would brainstorm recommendations for how can we reduce that risk to a more acceptable level. So might be to add another safety instrumented system or function, add a pressure relief valve, and so on. But I'm not here to teach you how to do a HAZOP. The purpose of this discussion is to talk about the HAZOP process and how we can then apply that to performing a cyber HAZOP or cyber risk assessment. But to finish this discussion, one thing I want to point out is that most industrial processes are protected by multiple layers of protection, most potentially hazardous industrial processes. Starting with the basic process control system, that's primary job is to keep that process under control flows and levels and temperatures and so on. If that process should deviate, normally the first thing that would happen is a process alarm will be raised, and an operator, human operator, will normally respond to that in a number of different ways, to potential different ways to bring that process back into control, back into a safe state. If the operator or the alarm should fail, then generally speaking, the next layer of protection oftentimes is something called a safety instrumented system, which is a separate control system that can monitor for unsafe deviations and can independently act to bring the process automatically back into a safe state. You may know these as emergency shutdown systems, or burner management systems, or fire and gas systems. They're all different forms of safety instrumented systems. Failing that, then we get into more, these are prevention layers, and we get into mitigation layers, which usually the first mitigation layer would be some kind of mechanical safeguard, like a pressure relief valve or a rupture disc, something that would mechanically relieve the pressure in this example. In this case, we're no longer preventing, but we are containing by letting that pressure relief valve vent. Hopefully we're going to vent to flare or something where we've had a loss of product, a loss of containment, but we are controlling and preventing anything more serious from happening. Beyond that, we have collection basins and emergency response. So the further you go up, of course, the less further you're away far from the ideal. For those of you who might not be familiar with safety instrumented systems, they are systems that, as I said, are there to monitor and bring the process back to a safe state. So we would normally have a basic process control system that's measuring values like pressure and performing some algorithms and calculating outputs to control, in this case, flow. The safety instrumented system is then a separate system that sits, you can think of it as on top of that, to, again, monitor those critical variables, typically using independent devices, and perform its own logic and algorithms and control outputs to devices that can bring this process back to a safe state, in this case, block flow. Challenge we have in modern control systems, well, first is that the PHA and the HAZOP process generally assumes that the control systems and the operators and alarms are able to perform their intended function, that they can act as an independent layer of protection. And they're generally given a fairly high probability of success. When we do something called a layer protection analysis, we actually assign probabilities to those systems being able to perform their intended function. And additional layers of protection are added when the risk of the control system alone and the alarms is too great. The challenge we have today is that modern control systems and safety systems are programmable software-based systems that are networked and oftentimes sit on the same network and communicate to the same Windows servers and workstations for engineering and for visualization, HMI, and so on of the process. So it is very, unfortunately, very possible that based on the design of the control system, that a single vulnerability on the process control network or a virus getting into the system, for example, could actually disable both layers of protection or multiple layers of protection, really, due to one cyber incident, such as a virus getting into the system or a storm on the process control network that might leave the operators blind, for example. So it does not have to be an intentional event, such as a hacker getting into the system. Certainly that is a threat, and if that were to occur, and for example these different workstations were compromised by outside or unauthorized access to these systems, they could potentially have the ability to completely override all the controls of the system. But it doesn't have to be a hacker. It could be, as I said, a virus that gets into the system or some kind of disturbance on this network that would also cause the same type of potential incidents, such as loss of view or even potentially loss of control. Going back to this diagram, the same type of visualization that one cyber event could potentially take out all three layers of protection. So how do we make sure that that doesn't happen? And that's just one scenario. Because we're generally talking about hazardous chemicals and hazardous industries that have safety systems. That's the example that I wanted to bring up. But there are other not as significant incidents that could happen in other applications, even with those without safety systems. They could, for example, shut down an entire facility due to a single cyber event. So how do we avoid that? Well, hopefully you have heard of the ISA 99 series of standards. It's a set of industry standards that have been under development since the early 2000s. It's actually now known as ISA IEC 62443 series of standards, but many people still refer to them as ISA 99, which is the committee that is writing the standards. And one of the earliest pieces of work from that standard is 990101, which was published in 2007. And it talks about the idea of a cybersecurity life cycle and how it's important that we take a life cycle approach to managing the risk of cybersecurity in our control systems, starting with an assessment of risk. So the first phase in the life cycle is to do an assessment and understand where are the risks, where are the gaps, and what level of security is needed for the different parts of the system. And this is primarily what we're talking about today, is risk assessment. Once the assessment phase is done, then we would move into an implementation phase where different countermeasures are designed and applied to the system to help mitigate that risk and bring reduce the risk or to achieve the desired security level. And then beyond implementation, then we would move into a maintenance phase where we would continuously test and deploy patches, antivirus signatures, maintain all our countermeasures, whatever they may be, access control lists and things like that. Also conduct periodic vulnerability assessments, and over time may need to implement additional security measures because, unfortunately, in today's environment, there's always new threats, there's always new vulnerabilities, and so a static security program will not suffice. You need to maintain that and fellowship over time. So, as I said, it's really important to start with the risk assessment phase because really before we can protect our control systems, we really have to understand what we are dealing with. What are the threats to those? What are the critical assets in our system that need protection? What are the realistic threats against those? What are the vulnerabilities in those systems or components that would allow those threats to be realized? And looking at that all together, then we can evaluate what is the actual risk that those assets or those threats pose to our operations. The basic formula for risk is threats, vulnerabilities, and the consequences. So by examining all three, we can come up with a good estimation of what is the risk. And by doing so, then we can start to rank the risks from highest to lowest and make sure that we're spending our money and our resources wisely to mitigate the high-risk items, but avoid spending our time and money going after what might appear to be high risk, but when you actually do the analysis, sometimes these things turn out to be not as high as one might think. All too often, we see in practice that companies often skip the risk assessment and jump right to solutions and start implementing, putting in things like intrusion detection and firewalls and different types of things like unidirectional gateways and access control systems and vulnerability management systems, and you name it. And not that those are bad things to put in. The argument is that before you start spending your money and applying technology, you need to first evaluate where are the where are the high risks, and make sure you're choosing the most appropriate technology to mitigate those risks, and you're spending your money in the right place and your time. Because everybody, most companies don't even have a cybersecurity budget, but if you do, it's certainly not limited, or not unlimited. And so that's my arguments for, of course, why it's so important. So then you can once you understand that, then you can start to develop a plan to address those unacceptable risk areas and recommend changes to not only technology but practices, policies, procedures, and so on. Determine the right priorities and balance the cost of countermeasures versus their effectiveness and the amount of risk reduction you'll get for each dollar you spend. Until you've done a risk assessment, you can't do that. And of course, this is not, the concept of performing risk assessments is not unique, and it's beyond ISA. The new preliminary cybersecurity framework that was published by NIST just a couple weeks ago, the National Institute of Standards and Technology, in response to the U.S. government executive orders that were signed earlier this year. NIST has now published what they call their preliminary cybersecurity framework. That is meant to be a framework that covers all critical infrastructure industries, everything from the financial industries to banking and finance to medical, transportation, oil and gas, water, wastewater, power, and so on. So it's a fairly broad set of framework. And the one thing I want to point out, though, is that while they don't necessarily call this a life cycle, the approach the framework talks about is different phases, starting with identify, protect, detect, respond, and recover. And in each of these 5 functions or phases, then there are different categories and subcategories of requirements and lots of informative references. So just like the ISA 99 security lifecycle, the NIST cybersecurity framework also starts with a risk assessment. Drilling down a little deeper into what NIST says in the area of risk assessment is, as I said, there are different categories and subcategories of requirements. And for each of those, there are numerous informative references. The framework is, as the name implies, a framework, not a technical specification or standard. So the framework is meant to guide asset owners in the process and point them towards appropriate informative references for the technical details. Now, the ones I've highlighted here are the ISA 99 references, and I did that because these are ISA 99 is the only industrial control system standards that are referenced here. Because the framework needs to apply across numerous industries, there are plenty of other standards mentioned here that are referenced here that are generally IT security standards and best practices. Things like ISO IEC 27000, NIST 853. If you're come from the IT world, you should definitely recognize these standards. 839 is a risk management standard, for example. But the only ICS cybersecurity reference is the ISA 99. In this case, it's 990201, which is a document that was published in 2009 by the American National Standards Institute, ANSI, as well as ISA for the U.S., and also internationally through the IC. So it's also known as 62443-2-1. And it has been available, as I said, since 2009 or 2010. And it is a ratified standard that can be applied today. So I wanted to recap what are the high-level risk assessment requirements from that standard. And basically it says You shall select a risk assessment methodology. You shall conduct high-level risk assessments. You shall identify all your control systems, and you shall have simple network diagrams for those, because like the HAZOP process, where you must have a good P&ID diagram to perform a cyber risk assessment, you must have good system architecture or network diagrams. You shall prioritize the systems that you're going to assess, and then perform detailed vulnerability assessments of those and detailed risk assessments, and then periodically reassess and throughout the life cycle, and finally, of course, document. The 99 standard in itself does not prescribe how to perform this risk assessment. The requirements are those that I just read to you, which are that you must do these things. There is an addendum or an annex to the document that does describe an appendix, I should say, sorry, that describes the process, an example process of how one might do that. And in a moment, I'll show you another one from another document in the series. But any good risk assessment methodology is going to have some basic steps. And that is understanding and identifying and characterizing the different types of threats against a system, the types of threat actors, which might be human or other computers, or even natural events, as well as the types of threats. Are they denial of service attacks? Is it a malware? Is it tampering? Then identify the critical assets and assess their vulnerability. How vulnerable are these to the specific types of threats that we've identified? With that information, then we can make some judgment call as to what the likelihood of that asset being compromised is. And then we can evaluate the risk by understanding the likelihood and the consequences. Then we want to look for ways to reduce that risk, particularly if it's unacceptably high, and prioritize our risk reduction measures based on a sound strategy. Unfortunately, it can be quite challenging to perform a risk assessment on a control system, particularly versus an IT system. And here are some of the reasons why. Number one is it can be difficult to identify all of the control system assets and assess the vulnerabilities of those. For a number of reasons. One reason is that oftentimes these systems are not well documented. The network diagrams might not exist, might be outdated, and so your diagrams may not necessarily represent exactly what is in the field and operational. Also, contrary to the IT enterprise environment, it's much more difficult to gather good asset management information. We often can't scan these networks for a couple reasons. One is because they're behind a firewall, hopefully, and they can't be reached by general corporate IT. But another reason is because it's not a good idea to scan these networks. The devices that sit on control system networks tend to be much more vulnerable and susceptible to network disturbances, like even simple things like ping sweeps and Nmap scans and Nessus scans can cause problems on a control system network that is responsible for high-value production and potentially dangerous production. So it can be very risky to run automated scanning tools on a process control network. So again, making it difficult for us to understand what those assets are and what we have in the field. And even if you could, vulnerability scanning tools generally are focused on Windows and other commercial operating systems and databases and so on. So they can only detect vulnerabilities in a portion of the equipment that might sit on our process control network. And devices like PLCs and variable frequency drives and smart motor control centers and so on often just are not supported by commercial vulnerability scanning tools. We have to find other ways to get this, to collect this information about our control system assets and those vulnerabilities, and that generally involves performing a vulnerability assessment, which is having a team of people with expertise in this area to be able to go into a facility and collect this information in a non-intrusive manner to identify the correct control system assets and configuration and the vulnerabilities that lie within. So difficulty number one basically is that you need to perform a vulnerability assessment to get started. Number two, another challenge is being able to determine the impact or the consequence of compromise. And this is where the PHA process can help greatly, because if we've done a PHA or a HAZOP, then we have information that says what are the hazards, what can go wrong in the process that could result in serious consequences, safety, environmental, and so on. So the missing link here, though, is how does the control system play into that? What are the cyber causes of the potential hazards that we've identified in our PHA? A PHA or a HAZOP is not generally going to look at the cyber causes. It would generally be beyond the skill level of the people who participate in a HAZOP, but also from a time management standpoint, HAZOPs are difficult and time-consuming enough that to just look at the basic deviations and causes, that it wouldn't be practical in most cases to drill down into all the different cyber causes. So what we need to do is perform our general, as we do today, perform our PHAs and HAZOPs and feed that information into a cyber PHA or HAZOP that would generally follow. So understanding the impact of those consequences can be difficult. For example, what would be the impact if an OPC server in a control system were to be compromised? If it were to either shut down, or if the information was actually compromised and the misleading values were being communicated throughout the system, for example, or if a PLC were to be compromised, or the engineering workstation, or the application server, and so on. So that's the challenge, and that's what would be resolved in a cyber HAZOP or cyber risk assessment, would be to go to again have a multidisciplinary team work together to systematically go through and discuss these the impacts and the threats and the vulnerabilities. And lastly, it can be difficult to estimate the likelihood or the frequency of events. We don't have a lot of data available today that talks about what is the likelihood that a virus might get into a control system. There's some information. For one thing, we know that viruses actually are the #1 cause of cyber control system incidents, but still estimating the likelihood or frequency can be difficult. So there's another document in the ISA 99 series that is in the process of being developed called 62443-3-2, best known as Zones and Conduits. And we are working in that committee on putting together a risk assessment process that can be used generically throughout industry to be able to perform a cyber risk assessment. And like I mentioned when I talked about good risk assessment methodologies, it has steps like identify threats, identify vulnerabilities, determine likelihood by looking at those threats and the vulnerabilities associated with those, determine impact referring to information coming from the HAZOP and then evaluating the impact, the cyber impact, and then ultimately calculating the risk and using the corporate or standard risk matrices to do so. So I'm going to walk you through quickly here with the remaining time an example that is part of the work process that my committee is working on in for the 3.2 document, which is to perform a cyber HAZOP or cyber PHA on a typical control system. So, as I said, you need to start with a good system architecture diagram. So this is a typical, relatively simple, again, system architecture diagram for a pretty typical control system that you might find in a facility today, where you would have one or more basic process controllers, PLC, DCS controllers, some servers to communicate between the controller and the operator stations, as well as some kind of an engineering workstation for configuration changes to be made. In this case, we're showing also a safety PLC or a safety instrumented PLC on the same network, which is pretty typical, and in this case, a separate engineering workstation for the safety system, but common operator stations for both. In this case, which is generally the case, is there is some kind of a boundary device between the business LAN and the control system. In this case, we're showing a firewall. And then there are other servers that sit up in the business, or they might be in a demilitarized zone, but could be either. Things like historians and domain controllers and other services that sit at the business level, but are actually communicating through that firewall to the control system. So this is meant to be typical of what is seen in industry today, but might not match exactly what you have. But the idea in this example is we want to go through that system and start to systematically break it down into, in this case, we would look at different nodes of the system, which would be the different either LANs or key servers or key elements of the system, and then look at the different deviations, what could happen to those nodes in the system, and then break it down further into the causes. How could that happen? What would be the threat or the threat actor that would cause that deviation, and what would be the consequence of that? So this is a relatively, you're seeing a portion of a relatively complicated example of a cyber HAZOP that was performed on a fictitious gas plant. The system has been broken down into the business LAN, a router that separates the business LAN from the PCN. We'll also look at the router to the corporate network, the operator stations, engineering stations, and actual PLC system buses, and so on. And so what you're seeing is a portion of it, because this tool that we used, called FACS, is a HAZOP type tool that has been modified or tweaked to be able to for cyber. And then we can look at the different cyber causes and consequences, and we can evaluate the likelihood both before and after safeguards or countermeasures. So we look at the unmitigated risk in this column. Then we evaluate what safeguards are in place to prevent that, are already in place to prevent this unwanted event, such as in this case antivirus protection, intrusion protection, and how does that impact the likelihood, and what is the then residual risk, the risk with the safeguards in place. There's a risk matrix that you can't see that would be behind the scenes that effectively looks up likelihood and severity, and provides a risk ranking and a numerical value for risk, as well as the color coding is being driven off of that risk matrix. So by using the color coding in the numerical system, you can quickly at a glance see where you have unacceptably high risk. And then the cyber HAZOP team would then brainstorm different types of recommendations or mitigations or countermeasures that could be put in place to then reduce that risk down to a more tolerable level. And then the next likely step in the process, once you get a number of recommendations, is that those need to be evaluated for both cost and effectiveness. There's not enough time in this short webinar today to go through the details of how to perform a cyber PHA specifically, but I can tell you that this process has been used successfully a number of different times, many times, throughout the process industries, particularly in oil and gas, chemical, air separation, gas plants, as you can see, pipelines, and so on. So it is a proven methodology that we have used many times successfully. And the objective is then, once we understand those risks and those high-risk areas by going through this process, that although it takes some time, it doesn't take a lot of time. Generally 1 or 2 days, you can evaluate a pretty large control system. But by going through that, then you can make very good informed decisions about how do I want to restructure the system, where do I want to put in my mitigation layers, how would I break this up into zones and conduits, a very important concept in the ISA 99 series. How do I intelligently break it into zones and conduits? Many times we see networks that have been partitioned, but not based on any good analysis. So this is showing you a potential output from the process that would say, based on risk assessment, we have decided that we need to zone off our safety system, for example, and then put in a firewall. And we might, of course, add different types of access controls to the system. We might even implement different policy and procedural type safeguards as well, as in addition to technical ones. But by going through that process, we can make those decisions in an informed way by following good engineering practice of analyzing and assessing risk, and then designing to design to acceptable, tolerable levels. It helps identify what plans and processes need to be addressed first because they represent highest risk to the corporation. The process can help you intelligently design and apply countermeasures such as segmentation, access controls, hardening, detection, and so on to reduce risk. But I emphasize the intelligently design because, as I said early on, there's a lot of technology out there that's available, and it can be overwhelming sometimes to decide what technology is best suited. And by understanding risk, you can make good informed decisions. You can prioritize your activities, your resources, as I said, because we all have limited budgets and time, and evaluate those countermeasures based on their effectiveness as well as against their cost and their complexity. So again, we're getting the most bang for our buck. We're spending our money wisely. And that is hopefully one of the takeaways you'll get from this webinar is that performing a cyber PHA or cyber HAZOP will make sure that you're spending your money and your limited resources wisely, and you have good documented evidence as to why you have made certain decisions, and good documented evidence as to why the corporation should spend the money and the resources to perform certain things. Because I think we all know that management there's a few things that the language of management is either financial or risk. And ultimately, I'll come back to financial. So by performing such a process and quantifying, semi-quantifying the relative risk, we can talk to our management and show them how we have done our homework and our due diligence in understanding the risks and quantifying them and putting forth solid recommendations based on prioritized risk reduction. So with that, I will take the remaining few minutes and see if you have any questions. We do have a Q&A here, and hopefully you'll see a tab at the top of your screen where you can type in your questions, and I will respond to them if I can. So I got one question here. What is the HAZOP team configuration other than a network specialist? That's a very good question. So the cyber HAZOP team is going to rely on a few key roles or specialties. You clearly need somebody from the operations side. That could be one of the lead operators, for example. People who understand the process and they understand the types of process upsets and the role of the control system. So you're also going to, excuse me, need a good automation person, somebody who knows the process automation of the DCS system. And you should also have people there that understand the health, safety, environmental type people or safety that can help quantify some of these things. As well, of course, IT. You should have a good network specialist and an IT security should be represented at the table as well. Another question here is, how do you determine the likelihood of the event? That's a really good question. So likelihood is generally broken up into, the best way to do it is break it down into a few different factors. I said earlier that the basic risk equation is for cyber risk is threats, vulnerabilities, and consequences. The likelihood part of it comes from the threat. What is the threat? Some people use the term the strength of a threat, meaning how capable is the threat, how determined is the threat actor, and threat and then vulnerability. In order for a threat to be successful, meaning for it to achieve its desired outcome, then there has to be a corresponding vulnerability in the system or the component that would allow that threat to be realized. And the vulnerability then can be looked at by evaluating the different components in terms of what countermeasures and security features are built in that would, or have been applied, that would be able to effectively block different types of threats. So I'll give you an example. A threat might be a virus getting into a server. So you would look at a few factors: is how capable is that virus? What are the different ways that it could get into the system? What are the access points? Could it be through a USB stick, through the network, through infected media, through a laptop plugged into the network? And then what is the vulnerability? Does that server have endpoint protection on it? Are there safeguards that would block, for example, are the USB ports enabled on that server? So you look at the two factors. You look at threats, you look at vulnerabilities, and you come up with a best guess, an intelligent best guess at what is the likelihood. But by breaking it down into the components of likelihood, you have a much better chance at arriving at a value that the team can feel comfortable with. We're not looking for precision here. We're looking for orders of magnitude. Generally speaking, we're going to rate likelihood on a scale maybe of 1 to 5, with say 1 being the highest, and that might be as frequent as once a day, once a week, to very low, which might be once every 30 years, once every 100 years. And you need to define a likelihood scale that has very broad ranges, and look at the threats, look at the vulnerabilities, and pick a value. As I said, it's typically going to be on a scale of like 1 to 5, 1 to 6, something like that. There's no prescribed method. The idea, the main thing is that you're consistent. Once you've set that scale, that you stick with that and apply that for all your different cyber HAZOPs. Great question. That is part of the challenge in conducting these, and why it's really important. In my experience, somebody asked about the team. I guess the one person I forgot on the team that's pretty important is actually a facilitator. And a facilitator ideally is somebody who's not in any of those different groups: operations, IT, engineering, production, for example, but a more independent, ideally an independent third party that is not going to have any bias towards any of the decisions, that helps facilitate and lead the discussion and drive the team towards agreement on things like likelihood and consequence selection. So that's actually a big part of what we at Exida do, is help conduct and facilitate these cyber risk assessments. One more question here involving the system vendor, considering their knowledge of system behavior, like package unit vendor for SIL selection. I think what the question is would it be important to involve the system vendor in the cyber HAZOP process? And I would say, yeah, absolutely, because they're going to have good knowledge about the behavior of their system, generally how their system would behave to different types of events. Having them plus the on-site automation experts that know more about their particular application of the system, plus the operations people who know the process, that would make for a very good cyber HAZOP team. So thank you for that comment. Well, we have reached the end of our time. I hope you enjoyed the webinar. I've put my contact information here. If you have any further questions that come to mind, don't hesitate to contact us. And as I said, you will receive a thank you email from us with information as to where you can view a recording of this webinar, as well as download a copy of the presentation materials. So, thank you. I appreciate your attendance.